Hello and welcome to this new lecture on stagnation properties. So we'll start this lecture by talking about the stagnation enthalpy. The stagnation enthalpy denoted by H naught. So as a definition, the stagnation enthalpy is the enthalpy of the fluid as it is brought to rest adiabatically. So it is the enthalpy of the fluid as it's brought to rest. So to rest, meaning that the final velocity will be equal to 0 adiabatically, meaning that there is no heat transfer between the fluid and the surrounding. So let's say we have this channel flow, a flow inside a channel, and the fluid is finally discharged into this very large tank where the final velocity will be equal to 0. And let's say that this channel along with the tank is very well insulated, so there is no heat transfer between the fluid and its surrounding. So here we have a fluid flowing at an enthalpy H and a velocity V, and the final velocity inside the tank V naught will be equal to 0, so this will correspond to a stagnation enthalpy H naught. Now let's take this control volume, and what we want to do, we want to apply the first law of thermodynamics on this control volume. So at the inlet of this control volume, the fluid will be entering at the enthalpy H and the velocity V, and at the exit of this control volume, the fluid will be exiting finally to the final velocity V naught equal to 0 and the stagnation enthalpy H naught. So the first law of thermodynamics for an open system, we will have the change of energy with respect to time is equal to the heat transfer with the surrounding minus the work transfer with the surrounding plus m dot into the change of enthalpy between the inlet and the exit of the control volume. So at the inlet we have the enthalpy H, and the exit we have the stagnation enthalpy H naught, plus the kinetic energy change between the inlet and the exit. So we have V square minus V naught square over 2 plus the potential change, the potential energy change Gz minus Z naught. Now here we have steady state conditions, and as we said, we have adiabatic conditions. So adiabatic condition corresponds to Q dot equal to 0, and here there is no work transfer of any kind between the control volume and the surrounding, so W dot will be equal to 0. And as we said, since the fluid will be brought to rest, V naught will be equal to 0. And let's say we don't have any change in elevation, so there is no change in potential energy. So finally, what we will have a relationship between H naught, the stagnation enthalpy, H, the enthalpy of the fluid, and V square over 2, the kinetic energy of the fluid per unit mass. So we can rearrange this equation and obtain that H naught will be equal to H plus V square over 2. So the stagnation enthalpy is equal to the enthalpy of the fluid plus the kinetic energy of the fluid per unit mass. Now for an ideal gas, we know that the enthalpy is related to the temperature by the following relationship. So H will be equal to the specific heat at constant pressure multiplied by the temperature of the fluid. So if we replace this relationship in this expression here, we'll have Cpt naught is equal to Cpt plus V square over 2. And if we divide both sides by Cp, we'll have T naught is equal to T plus V square over 2Cp. So this is a relationship relating the stagnation temperature of the fluid to T naught to the temperature of the fluid and V square over 2Cp. So this is T naught is the stagnation temperature T naught, and also it is defined as the temperature of the fluid as it is brought to rest adiabatically. So this is the temperature of the fluid as it's brought to rest brought to rest adiabatically. Now, please pay attention here. The only condition that we have is the adiabatic condition. So in this equation, we have assumed an adiabatic process. And also we can say that this equation can be applied to frictional and also can be applied to frictionless process. So the assumption of a frictional or a frictionless effect is not present in this equation. So the definition of the stagnation enthalpy or the stagnation temperature is valid also for adiabatic frictional flow, and it is also valid for adiabatic frictionless flow. So please know that for adiabatic plus frictional meaning irreversible, or adiabatic plus frictionless, which is reversible. So adiabatic plus frictional, we can say this is an adiabatic non-isentropic flow. So for an adiabatic non-isentropic flow, we know that from an entropy balance, the entropy will increase due to the presence of frictional effect or due to the presence of irreversibilities. And for the second condition, adiabatic plus frictionless, simply this means isentropic flow. Isentropic flow. And if, let's repeat. If we go back to the definition of the stagnation enthalpy, this is the enthalpy of the fluid as it is brought to rest adiabatically. We don't have an additional condition regarding the presence of a frictional effect or not. So for both cases, regardless if we have a frictional effect present or not, we will have the same stagnation enthalpy and the same stagnation temperature. So to clarify this, if we draw a process, the process on an HS diagram, an enthalpy entropy diagram. So starting from a given fluid at some condition, we have the fluid at the enthalpy H and some entropy S. So if we bring this fluid to rest isentropically, let's say, we will have an increase in the enthalpy. And here, since we're talking about an isentropic process, the entropy will remain the same. And finally, the fluid will reach the stagnation enthalpy H naught. So this is an isentropic process. Now for an actual process also, what will happen to the entropy? The entropy will increase, given that we have adiabatic conditions. So this is an actual process. Adiabatic, in other words, this is an adiabatic plus a frictional process. So friction will cause the entropy to increase. However, at the stagnation conditions, we will have the same value of the stagnation enthalpy. Okay, so if we look at the pressure, so starting the fluid having a pressure P, following the isentropic process, we will have the stagnation pressure P naught. However, following the actual process, we will have a stagnation pressure P naught actual, which is smaller than the isentropic stagnation pressure. So this is the isentropic stagnation pressure, which is greater than the actual stagnation pressure. And why? If we look at the definition of the enthalpy, we know that the enthalpy is the summation of two energies, the internal energy plus the flow energy P over rho. So what will happen for the same stagnation enthalpy, friction will cause the internal energy of the fluid to increase. So friction will cause the temperature of the fluid to slightly increase, and as a result, the flow energy of the fluid will decrease. So this will be manifested by a decrease in the pressure. However, the summation of the two will be the same, which is equal to the stagnation enthalpy. Okay, now if you want to look at the definition of the stagnation pressure, we're talking mainly about this isentropic stagnation pressure. So for the stagnation pressure, it is the pressure of the fluid as it is brought to rest isentropically. So this is the pressure of the fluid as it's brought to rest isentropically. So for the stagnation enthalpy and the stagnation temperature, there is no difference between adiabatically and isentropically. Eventually you will reach the same values. However, for the stagnation pressure, you need to pay attention. The stagnation pressure is the pressure of the fluid as it is brought to rest isentropically. Since for a non-isentropic process, as you can see here, you will reach a stagnation pressure that it is smaller than the isentropic stagnation pressure. So please pay attention to these differences. Now, what we want to do, we want to obtain a relationship between the stagnation pressure and the stagnation temperature T0. So to do this, we said that for an isentropic process, for an isentropic flow, let's say, PV to power K is equal to constant. We have this polytropic relationship. And in terms of the density, we can write it as P over rho to power K is equal to constant. So for the same constant, we can say that P over rho to power K can be equal to P over rho to power K at the stagnation conditions, which is P0 or P0 over rho naught to power K. So let's rearrange this equation and we'll have the ratio P0 over P is equal to rho naught over rho to power K. Okay, now what we want to do, we want to obtain a relationship between the ratio of P0 over P to the ratio of T0 over T. So to do this, now to continue, we will apply the ideal gas law at the stagnation conditions, which is P0 is equal to rho naught RT0, and at the static conditions we will have P is equal to rho RT. So if you divide the two equations together, you will have P0 over P is equal to rho naught over rho into T0 over T. So in this case, rho naught over rho will be equal to P0 over P divided by T0 over T, or simply multiplied by T0 over T to power minus 1. So let's replace rho naught over rho in this expression here. So we'll have P0 over P is simply equal to P0 over P to power K into T0 over T to power minus K. So now we will have, if we divide P0 over P by P0 over P to power K, we will have P0 over P to power 1 minus K will be equal to T0 over T to power minus K. Now let's raise to the power 1 over 1 minus K both sides. So we will have P0 over P is equal to T0 over T to power minus K over 1 minus K. Now if we multiply the numerator and the denominator by minus 1, we will have simply P0 over P is equal to T0 over T to power K over K minus 1. So this is a relationship relating the ratio of the stagnation pressure to the pressure and the ratio of the stagnation temperature to the temperature of the fluid. Now also to obtain a relationship between the ratio of the stagnation density and the density of the fluid to the ratio of T0 over T, we simply can use the following relationship here. So instead of P naught over P, if we replace it by T naught over T to power K over K minus 1, we will have, so here, rho naught over rho to power K, as we said, it is equal to P naught over P. So it is equal to P naught over P, which is equal to T naught over T to power K over K minus 1. So if we raise to the power 1 over K both sides, we will have rho naught over rho is equal to T naught over T to power 1 over K minus 1. So this is the relationship between the ratio of the stagnation density to rho and the ratio of T naught to T. So why we are trying to obtain a relationship between the stagnation pressure and the stagnation temperature, or the stagnation density and the stagnation temperature? Because if we go back to this equation here, you can see that for a given stagnation temperature T naught, as the fluid is increasing in velocity, as the velocity here V will increase, what will happen to the temperature? The temperature will decrease for a given stagnation temperature. So what we will try to do in the next video, we'll try to obtain a relationship between the ratio of T naught to T and the Mach number using this expression here. So if we obtain a relationship between T naught over T function of the Mach number, so in this case we will know the variation of temperature with respect to the variation of Mach number, and if we use this expression and we plug them in here and here, we will also obtain a relationship between the ratio of P naught over P function of, since we have obtained a relationship between T naught over T function of the Mach number, so this can be written in the same way, P naught over P function of the Mach, and here rho naught over rho function of the Mach number. So in this case, we will know the variation of the pressure with the Mach number and the variation of the density with the Mach number. So let's see how to do this in the next video, and let's try to obtain some important Mach number relationships.